All right, let's talk about fixed points and stability of nonlinear autonomous systems. So 5.2, we focused on linear autonomous systems, and now let's focus on nonlinear. And the application actually is in 5.4, so sorry, I think I mentioned last class the next section, but forgot we have to cover this one first, and then we get to 5.4 next week. So when we're talking or handling nonlinear autonomous systems, we are going to use something called the Jacobian Matrix. So this might be a little different. You do partial derivatives in Calc 3, which I don't remember what the prereq to differential equations is, but it's either Calc 2 or Calc 3. So most of you are either in Calc 3 or have taken it already, so hopefully you're familiar. If not, it's okay. It's really not that bad. So the Jacobian matrix is made up of, it can be as big as it needs to be depending on how many variables. The variables, however many variables you have, you'll have columns, and however many functions in the system you have, you'll have rows. So notice if f was the first function listed in the system, then this is saying take the derivative of the f function with respect to x, which means we ignore the terms of y and we only take the derivative with respect to x being the variable, and y is considered a constant, so the terms disappear. And then here we're looking at the same function, but this time we're focused on y as the variable and x being a constant and going to 0. Okay, and we'll practice that. So when we evaluate the Jacobian at each fixed point to get as many matrices as there are fixed points, finally we can then determine the stability of each fixed point. So we have to find the Jacobian first, and then we plug in each one of the fixed points in order to make decisions on the point stability. Partial derivatives. So let's take a look with examples of what I was saying when you focus on just one variable over the other. So here we're focused on the f function and with respect to x. So that means that y is just a constant, making this whole term go to 0, and the derivative of 4x is 4. Now the partial derivative of this function with respect to y, this one would be treated as a constant and would go to 0, and you would do 4y as our derivative. Okay, another example focused on x. Notice that x is in both of these terms. Everything else is treated as a constant, so we get negative 4x cubed. And here, x is to the first power, so we know that the derivative of an x term to the first power is its coefficient. And since we're treating 5e to the 2y as a constant coefficient, that's why that makes the derivative of that term. Flipping the script over here to the same function, but with respect to y, this term is constant, goes to 0. We're only focused on this one now. So the derivative of e to the 2y is e to the 2y times the derivative of what's inside, which is 2. That's using the chain rule, which is where we get the 10 from. So the 2 comes down in front and gets multiplied by the 5x, which becomes 10x. All right, let's put this all together. Again, if you haven't noticed, the reason why we need the Jacobian matrix for nonlinear is because linear, we know, goes through the origin, and nonlinear, not so... not necessarily just through the origin, which is why we need to find the fixed points and then use the Jacobian matrix to determine the stability of those fixed points. So let's do this example. I'm going to switch over to the whiteboard to give myself more room. All right, so we're working with the system x prime. Oh, let me use black. X prime is equal to x plus y, and y prime is equal to y cubed minus y. And again, we know this is nonlinear. Hopefully this is not brand new to you, why it's nonlinear, because you have that y cubed, which is not a linear function. All right, so step 1, let's find all fixed points. In order to do that, we can just use our calculator to do some of this work for us. Again, for work on an exam, make sure that you write what you typed in your calculator so I can give partial credit, because if you just write the outputs and they're wrong, I can't help you. You need to have work. So you're going to show me, you're going to use the solve feature in your TI-89. So I don't have an 89 in front of me, so I can't even show you in the camera. So the solve feature is under the algebra, which is like F2, I think, if I remember right. So we're going to solve, and you're going to type x plus y equals 0. Put in a space. Okay, there is a space button on your TI-89. Find that space button and press it. Type using your alpha keys and another space. Y cubed minus y equals 0, comma, and then you're telling the calculator solve for both x's and y's. So when we press enter, we get this output, x equals -1 and y equals 1, or x equals 0 and y equals 0, or x equals 1 and y equals -1. So that's the output. So we know our fixed points are -1, 1, 0, 0, and 1, -1. So we have 3 fixed points. Kind of nice that our calculator will do that for us, makes it simple. But now we need to do the work. Now we need to do the Jacobian part for these fixed points. So let's clear this out. First thing we want to do is find the Jacobian. So recall that the Jacobian matrix is comprised of the partial derivative of one of the functions with respect to x. The second component here will be the partial derivative of that function, but with respect to the other variable y. And then the second function with respect to x, and the second function with respect to y. Again, notice that each column is for the variables, while each row is for the system, the equations. Now, let's put our system back in front of us. So we have x prime. Let's let that be the f function. And that one was x plus y. And let's let y prime be the g function, which was y cubed minus y. Now, taking the derivative with respect to x in the first, the f function, well, we have x here, and the derivative of x is 1, and y is constant, so it goes to 0. And then taking the derivative with respect to y, we get the same thing. We get 1 because the x will go to 0. In the g function, taking the derivative with respect to x, well, there isn't an x in the g function, which means the derivative is 0. And if we're looking at the g function with respect to y, we get 3y squared minus 1. Now we can use this Jacobian matrix for each of the fixed points. So now I'm going to find the Jacobian at the first fixed point, -1, 1, which is literally substituting in any of the variables in the Jacobian. So 3 of the elements are fixed. We don't change those. There's no variables. The fourth component is the one that has variables, and it only needs the y value. So we put in 3 times y squared minus 1, and that gives us the matrix 1, 1, 0, 2. And we repeat this process for each of the fixed points. So now I'll do the 1, -1. Okay, so that gives us 1, 1, 0, 3 times -1 squared minus 1. Since the -1 squared is a positive one, no surprise, this Jacobian matrix produces the exact same matrix as the last one. And finally, we have the Jacobian of the origin 0, 0. And when we substitute that in, we get 1, 1, 0, 3 times 0 squared minus 1, which gives us the matrix 1, 1, 0, -1. Okay. Now that we have our Jacobian matrices for specifically the fixed points, we then follow the same process that we did in the last section with finding eigenvalues and then determining the stability based on the eigenvalue output. So since we only have two matrices to play with, the first one was 1, 1, 0, 2, which was produced by two of those fixed points. So we find the eigenvalue of this matrix, and we find that the eigenvalues are 1 and 2. Okay, so we see that there are two real eigenvalues, and they're both positive. And so that means that the fixed points 1, -1 and -1, 1 are a source and unstable, which you can go back to 5.2's PowerPoint for all of the references on those conclusions. Then let's take a look at the fixed point 0, 0. That matrix was the matrix 1, 1, 0, -1. And we find the eigenvalue of this matrix, and we get 1 and -1. So we see that there are two real eigenvalues. They are opposite signs, though. Okay, so we have one real eigenvalue that is greater than 0 and one real eigenvalue that's less than 0. Therefore, the fixed point at the origin is unstable and a saddle. And that's it. That is taking nonlinear systems using a Jacobian matrix in order to find the eigenvalues to determine stability of those fixed points.